Welcome to Spring LIB.
In this exercise, we have a spring that has a spring constant K and an unstretched length L0 that is connected to a block A that has a mass MA, and block A in its turn is next to block B that has a mass MB. Now block B is pressed against block A, making the spring be compressed by a distance D. And then the two blocks are released. Our goal is to find first what is the distance x that the two blocks will travel before they begin to separate. And then using this information, we have to find what is the velocity of the blocks when they begin to separate. Okay, so what we need to do here is to draw the force diagram, the free body diagram for both blocks. And in order to do that, first we need to remember how we calculate the force, the elastic force coming from a spring. So the force is equal to minus K times delta X, where the minus sign is here to guarantee that the force is contrary to the direction of compression. So if the spring is compressed, okay, if the spring is compressed, then the force acts in the direction that is opposite of the compression. And if the spring is stretched, then the force also acts in the opposite direction as the stretching. Okay, so this is the elastic force. Now let's draw the free body diagram for A and B. So for block A, here's block A. Okay, this is the spring that has a length L0. Okay, this is the length L0. This is the length by which the spring was compressed, D. And let's consider, and after, at this point here, the block has a speed V equals 0. Then it travels a certain distance, which I'm going to call X. Let me draw it a little differently. This here is X. So notice that the force that act, this here is D minus X. Notice that the force that acts on block A, the magnitude of the force, is equal to K times D minus X, and the force points in the positive direction. Okay, and I'm setting the positive direction should be to the right. Okay, so we have a force that is pushing the block to the right. We also have the force of that block B exerts over block A, and I'm going to call this force N. So we have that F minus N is equal to the mass of block A times the acceleration of block A. Now F, as I said, the magnitude of F is K times D minus X minus N, and this is MA times A. Okay, so now let's draw the free body diagram on block B. So this here is block B. And the only force acting on block B is the force that block A exerts on block B. Now, according to Newton's third law, this force must be equal to the force that block B exerts on block A. Okay, so we have that n is equal to mb times a. Since the acceleration of block A and B are the same when they are not separated. I'm going to take these two equations here, actually this one here and this one here, and I'm going to sum them. So we obtain k times d minus x, the n's cancel out, and this is equal to ma plus mb times the acceleration a. So the acceleration a is equal to k times d minus x divided by ma plus mb. Okay, this is the acceleration. And we can also find the force N just by substituting the acceleration into this equation here. So we have that N is equal to mb times the acceleration, so mbk d minus x divided by ma plus mb. Now notice that the force between block A and block B is 0 when x is equal to 0. I'm sorry, x is equal to d. So when x equals d, then the force that block A exerts on block B and vice versa is 0. Now notice that when this force is 0, then the two blocks are beginning to separate. So this is the answer to the first part of the question. The blocks start to separate when x is equal to d. Now we can find what is the velocity of the blocks when it starts to happen. So what I'm going to use is that the acceleration is equal to dv dt. I'm going to multiply both sides by v, so we have a times v is equal to v dv dt, and I'm going to write v as dx dt. So I have a dx dt is v dv dt. The t's cancel, and we're left with a dx is equal to v dv, and we have to integrate it from the initial velocity, which in our case is 0, to the final velocity, and in the left-hand side, from the initial position, which I'm going to call 0, to the final position, which is d. Okay. So the acceleration, the acceleration to be k times d minus x divided by ma plus mb dx, and this is v squared over 2. So we can solve. We have k times d times x minus x squared over 2 divided by ma plus mb from 0 to d, and this is v squared over 2. Okay, so this is k times d squared over 2 ma plus mb, and this is v squared over 2. The 2's cancel out, and we get that v is equal to the square root of k d squared over ma plus mb, which concludes our exercise.